Hi, welcome to Instrumental Analysis. I'm Vicki Colvin. This is the last mini lecture in a series that we're using to cover error in analytical measurements. Now, what this lecture is going to be about is how to use error bars. So by now you should be pretty comfortable understanding how to define the uncertainty in a measurement, whether you're doing that with replicate measurements or whether you're using more sophisticated tools or whether you had to propagate the error to get at that. However you got to your error bars, how do you use them? What are some of the common ways in which we can actually understand more about our data from having a good understanding of our random error? So we're going to cover briefly two topics today. One is dealing with systematic error. You might have recalled way back in lecture 4, I introduced both systematic error and random error, and we spent the last 3 lectures only talking about random error. Well, today we'll talk a little bit more about systematic error. And also the age-old question of, can I throw out a bad data point? If you are doing replicate measurements, when is it possible to throw out a data point? While that doesn't exactly use an error bar, it uses some of the same concepts that we used in defining the confidence limit earlier. So just to review where we've been, precision is a central issue to communicate when you communicate the results of a measurement. We learned about significant figures and instrument tolerances as kind of a way to estimate and sort of a shorthand way to convey to a reader how much information and how much precision might be in a number you're providing. Then we learned about doing replicate measurements and taking the standard deviation and using a plus minus bar, which we call the error bar or uncertainty, to convey the spread in the measurements. Then we talked about combining error and finally about reporting error in terms of a confidence limit, which takes into account both how many measurements led to our error bar as well as how confident we are that the true value lies within the bounds that we provide from the errors. So let's get into how we use error bars, however it is we arrived at them. One of the most common uses for error bars is actually to handle and decide if systematic error is present. So systematic error is much trickier to handle than random error. With random error, we can simply do replicate measurements and look at our data and characterize random error. But how do you know if you have systematic error? It's kind of insidious. There's one tried and true way of knowing if you have systematic error, and it's a fundamental principle in any quality control work in an analytical lab. And that is you buy a standard reference material, ideally from NIST or some other reputable standard source, and you do your analysis on that standard. Now that standard will come with a very precise, defined concentration, weight, whatever it is in your measurement. And by running your exact method on a known sample, you can characterize systematic bias. And that's a really important thing to do. So it's very common to actually include what's called a validated sample in any kind of normal analysis. And later when we get more into lead, you'll see that that's actually written up in the EPA and other procedures for measuring lead in toys. You actually have to have a standard material that you run on. And that's there to account for and detect potential systematic error. Conceptually, what we're going to do then is, first off, whenever you do a measurement, even if it's of a known standard, you're still going to have a spread in your values. And so that's going to be your error bar. So even though it's a known standard, you're not going to get the same number over and over again when you measure it. You're going to get a range, you're going to have a spread. So you have to have that spread. And the real question is then you have the true value. And is the true value within the spread that you have, or is it outside the spread? And here's how you quantitatively determine if it is or isn't. First, you're going to run the systematic error and you're going to characterize through replicate measurements an error or a spread of values. Then you're going to ask, how confident am I that the value, the true value, is the same as the pooled measurement set that I took? Because it's, it may not be the same. It may be a little bit outside, but you can't know for sure or with a certain given confidence until you've corrected for that. So what you're going to do then is you're going to actually calculate the confidence limit that they are the same. So you're going to take your average minus the true value, divide it by the standard deviation, multiplied by the number of measurements you made. You're going to compare that t-value, which is your calculated t-value. So this time, remember, you're not looking up a t-value, you're calculating a t-value for a given example, which is the true value part of my measurement pool or not? Once you calculate that, if it's less than the t-value you look up in the table, then yes, you can say there is no systematic error. The true value is contained within my data set. Or the converse is that actually the true value is too far outside the data set, and you actually find that it is greater than that, and then you cannot conclude that. So here's sort of mechanically what you're going to do. You're going to calculate the t-value for your data sets, in effect calculating a t-test experiment, if for those of you who've had more statistics. You're going to compare that to a t-table that a t that you pull from the table for a given confidence limit, typically 95% if it's not specified, and however many measurements you made when you measured the standard sample. If the experimental t is less than the t in the table, then you're good to go. You have no systematic error. If it isn't, you conclude that your true value is actually outside the range of your measurements, and that's an expression of some sort of systematic error. By convention, as I said before, if you haven't been given a confidence limit and you're just asked, is there evidence of systematic error, you're going to go for a 95% confidence limit. It's just kind of a convention. So let's do this quick example. So what this example is telling us is that you've bought a standard, which is 20%, and this is typical way to figure out if you have systematic error. So by buying a standard, they're certifying a value of 20.00%. This is the truth. So the question is, are these values that you did your measurement, are they likely to include the truth or not likely to include the truth? And specifically, are they 95% confident to include the truth? And if they are not, there's a systematic error. And if they are, then you can attribute the difference between 20.06 and 20.0 simply to some sort of random error. So here's how you go about doing this. First is that you're going to calculate your t-value rather than looking it up. So you're going to have what we call t experimental. And that's given here. It's the average of your measurements minus your true value divided by the standard deviation times square root of n. Then what you're going to do is you're going to look up the t, which is basically telling you the t that you can tolerate for 95% in n. And if your t is less than, then yes, the two are the same data set. And if they're not, then they're not. So let's do this. Now it's just a plug and check problem. Let's calculate t experimental, 20.06 minus 20. Notice the absolute values divided by the standard deviation times root 6. And look at this, we get 5.9, which is greater than the t we got from the table. So we looked that up from the t table. And so as a result, we know that there is, yes, systematic. I want to give you one other example of a decision, and this is a little bit, you don't exactly use the error bar here, but use some of the same ideas, and it's such an important idea I wanted to make sure I at least mentioned it. So often when you run replicate measurements, you'll get some measurement which is just way out of whack. So say you're measuring chloride content, like in that last example, you'll get 20.00, 20.01, 20.02, maybe a 19.9, and then all of a sudden you'll measure 15%. And then you'll go back to measuring all these normal values. And so the question is, can you toss out the 15%? Can you just say that's an outlier, that something happened when I collected that and it's statistically not relevant to the pooled data? And that's a really tough thing to do. And there's certainly a school of thought that says under no circumstances should you ever toss a data point. However, there's also a school of thought that says, you know what happens? Sometimes you get an outlier, you get a glitch, something happens, and that data point is different than the rest. You can't just willy-nilly throw it out because it seems like it's not right. You have to have an objective way to make that assessment. And that's what I'm going to explain now. It's called a Q-test. So what you're going to do is you're simply going to take the outlier. You're going to put all of your values in range of smallest to largest, let's say. Say your outlier was the 15%. You're going to take the difference between the 15% and the next lowest value in that chain. That's called the gap. You take the absolute value of that. And then you're going to divide it by the full range of all of the measurements. And then you're going to get a fraction because the full range is almost always going to be bigger than the difference between Q1 and that. And if that fraction is large enough, then you can actually reject it. So if the gap is so big and it's such a big fraction of the total range of the data, so say here's your gap and here's your range and this is your outlier, well, then you can probably throw it out because the Q might be 0.7, 0.8. And so what you do is you calculate Q and then you use the table shown here to help you decide. So say you did 5 measurements and you want to throw out a Q, an outlier that has a Q of 0.64. So, or say 0.8, well, you can, because if your Q is larger than the number shown in this table, you're allowed to throw it out. This is a subjective decision made quantitatively, and you should never do this without really thinking through if there's a logical reason to expect that you would have an outlier. And so if you have a very large gap, Q is going to be approaching 1. And the gap can be smaller as you get to bigger N because you're going to have more information about what the spread in the data is going to be. And if you relaxed your Q test to be a 70% confidence that you are okay throwing it out, then actually all of these numbers would go down a little bit. So there would be a less stringent test than there is if you've got a 0.76. If you have a 0.76, you're basically saying the difference between my outlier and the rest of my data is pretty much 75% of the full range of the data. And that's a pretty stringent test. So in any case, I'm not going to do an example of this because it's relatively simple to do. I will point you to the website at the bottom of the page. They have a bunch of nice examples of this and a pretty good discussion about how to do it a little bit better. You know, the problem with this Q test is you really only use 2 data points in the calculation of the gap. And there's much better statistical ways of making this assessment. But this is a pretty standard run-of-the-mill conventional thing that's taught in upper division analytical chemistry classes. So I wanted to make you aware of it and drill into your head. You can't toss out a data point unless you've applied the Q test and found that indeed the Q of the outlier is greater than the Q values from the table. So that brings me to one of the 2 examples I wanted to talk about, how to figure out if there's systematic error in a data set and when to toss